Hello and welcome to the Foundations of Artificial Intelligence. My name is Dr. Ryan Urbanowicz and I'm going to be the primary course instructor for this class. Today we're going to cover the course itself, the syllabus, some background about artificial intelligence, and we're also going to talk about some software they're going to use throughout the class and that you might use in the future if you stay involved with machine learning or artificial intelligence. Okay, so again, welcome. We have this cartoon to start, says, let's solve this problem by using the big data none of us have the slightest idea what to do with. And this should resonate if you're in the biomedical research community. This is a challenge a lot of us deal with. And it also speaks to the underlying purpose of this course, which is to lay the foundation for students to be able to organize, represent, interpret, search, and apply biomedical data in order to derive knowledge, make decisions, and ultimately to make predictions if we're using something like machine learning. So here's an outline of today's lecture. I'm going to start by introducing myself, then we'll talk a little bit about what artificial intelligence is and what are the focuses of this course. We're going to review the course syllabus, then we'll introduce Python and Anaconda and talk about how to install them. We'll talk a little bit about coding environments, some about Jupyter Notebooks, which we'll use in this course to complete homework assignments and some of our projects. So to introduce myself and my educational background, I started by getting a bachelor's of biological engineering at Cornell University and then a master's in the same also at Cornell. Then I moved to Dartmouth College where I got my PhD in genetics, and I stuck around to get to work on a postdoc in biostatistics and informatics. Later I moved to UPenn and started as a research associate in informatics. And now currently I'm an assistant professor here in informatics in DBEI. I'm also a senior fellow in the Institute for Biomedical Informatics and a part of two graduate groups, Genetics and Computational Biology, or GCB, and Epidemiology and Biostatistics, also known as GGEB. Some of my content area specialties include artificial intelligence, biomedical informatics, clinical research informatics, complex systems, data mining, genomics, machine learning, simulation, rule-based systems, and visual analytics. Okay, so what are my goals as an instructor? Well, first off, I want to make sure to try and clarify why we're learning each topic, to give you the context and the motivation to pursue understanding all of these things. I'm going to try primarily to present these topics from a conceptual perspective, but also provide opportunities for students to apply these topics in silico, or in the computer. I welcome feedback from students throughout the year. I'm always trying to make this course better. I want to make sure that you're getting the most out of it. Anything I don't know the answer to, I'll do my best to track it down. And of course, my goal is to improve this course this year and beyond. So if students have feedback in terms of clarity, or you find useful resources, or you have ideas on how to make it better, please let me know, because I definitely want to incorporate as many new ideas into this course to improve it this year and in the future. What are my goals for students? So I'm hoping you'll develop an understanding and appreciation for the unique challenges of representing and applying human knowledge within a machine. Also, it'll be important to understand the conceptual differences between deduction and induction and the role of both in artificial intelligence. Also, to develop an understanding and appreciation for what it takes to develop an expert system for real-world application. And we'll learn about expert systems a lot throughout this course. And lastly, to learn and apply the basics of Python coding and Markdown, just so that you have some hands-on experience with these things if you don't already. Okay, so what is artificial intelligence, or AI? So if you Google AI, you look at the world of industry or business and what they think of when they hear the term AI, it'll likely conjure images like this, right? You have images that combine very technological or computer science-based imagery with that of the human brain. And then if we turn to the entertainment industry, we're flooded with images of robotics, evil robots bent on destruction, benevolent robots trying to save mankind, right? But often we see these themes of autonomous, intelligent entities that develop sort of self-awareness and the capability to think like a human being. And so this conjures worries, right, about the future of AI and what it could turn out to be. And so on the chalkboard here, we have an instructor pointing out to the machine, good, cure cancer, or bad, take over the world. And the machine says, Sure, I promise. Can you hook me up to the internet now? Right? So there's this there's this underlying dread that if we ever do successfully create a true artificial intelligent entity, that we don't know whether it's going to be good or bad, right? And so this concern speaks to this idea of a technological singularity, also known as just the singularity. It's a hypothetical point in time at which technological growth becomes uncontrollable and irreversible, resulting in unforeseeable challenges to human civilization. Another way of looking at this is to think of it as an intelligence explosion, where you have an upgradable intelligent agent, like a robot, for example, that will eventually enter a runaway reaction of self-improvement cycles, each new and more intelligent generation appearing more and more rapidly, causing an explosion of intelligence and resulting in a powerful superintelligence that quantitatively far surpasses all human intelligence. And so this worry conjures very reasonable concerns about our ethical responsibilities as researchers developing artificial intelligence systems. And so we got this great quote from Jurassic Park: "Your scientists were so preoccupied with whether they could, they didn't stop to think if they should," right? And in fact, if you go to AI conferences, inevitably people ask these questions and people are concerned with this issue. However, while there are a lot of famous and very intelligent doomsayers that worry about the future of AI, including Elon Musk, right, who has his concerns, most people working in AI, like myself, have a hearty skepticism for the idea of the singularity. We know how hard it is to get even a little intelligence into a machine, let alone enough to achieve recursive self-improvement. So the point of this is that, while it's very reasonable to have concerns about where AI could go in the future, if you worked with it, if you've done a lot of hands-on work, and if you follow the literature, it's really hard to get basic artificial intelligence to improve, even on the smallest, simplest tasks, let alone develop self-awareness and everything else that might go into this idea of a singularity occurring. Now that we've had some fun with AI, let's talk about some of the traditional definitions of artificial intelligence, also known as machine intelligence. So our first definition is intelligence demonstrated by machines. In other words, machines are computers that mimic cognitive functions that humans associate with the human mind, such as learning and problem solving. Another definition, machines that behave as though they were intelligent. This is from McCarthy in 1955, one of the fathers of artificial intelligence. Here's another one, the ability of digital computers or computer-controlled robots to solve problems that are normally associated with higher intellectual processing capabilities of humans. Another, the study of how to make computers do things at which, at the moment, people are better. And lastly, getting computers to do tasks that require human intelligence. Right? So these are all reasonable but slightly different definitions of AI. So there's a common theme that emerges here where we have this idea of getting computers to do things that humans are normally capable of, doing it faster, more effectively, but basically mimicking humans for the most part. So the field of AI is influenced by a lot of other fields of study. So AI is mostly founded in computer science, mathematics, systems science, but it also has a strong overlap with the field of cognitive science, as well as a number of other fields including neuroscience, anthropology, philosophy, psychology, linguistics, physics, social science, and biology. This is a Venn diagram I created a while back in an attempt to become Twitter famous. Sadly, I did not. But anyway, this Venn diagram is meant to illustrate how all these terms you might hear if you get involved in machine learning, AI, or informatics in general, how all these terms come into play and how they subsume one another. So here on the left, we have the larger field of mathematics, of which statistics is a subfield. On the right, we have the larger field of computer science, of which artificial intelligence is a subfield. The term artificial intelligence shouldn't just conjure imagery of a machine that's become self-aware and super intelligent. Artificial intelligence means a lot of things, right? It covers lots of really basic computer science as well. And notably, the field of machine learning is actually a subset of the field of artificial intelligence. And machine learning includes things like supervised, unsupervised, and reinforcement learning, which we'll touch on in this course as well. At the overlap of these fields, we have terms like data science, data mining, as well as data analysis and pattern recognition. Okay, so before we move forward, it's worth taking the time to define what machine learning is a little bit more carefully to help differentiate it from the larger field of artificial intelligence. So, machine learning includes computational strategies that, given data, are designed to progressively improve performance on a specific task without being explicitly programmed. Artificial intelligence in general can also include situations where you're just trying to pre-program an automated response, and there's no learning that takes place. Literally, you could just have a bunch of if-then loops in a computer, and that could technically be considered artificial intelligence. So machine learning also notably includes many, many different methods or algorithms. Sometimes I go to conferences and I hear people accidentally mistake machine learning for being the exact same thing as something like deep learning or neural networks. And so those are just, a couple examples of machine learning algorithms. And of course, machine learning is a much broader area of methodology. The big picture goal of machine learning is to learn useful generalizations. To illustrate this, we have some examples of some specific trees, and we're trying to identify, in general, what does a tree look like? How do we classify a tree? So when we see a specific tree in the future, we know we have sort of a model of what defines a tree so that we can separate out maybe trees from cars, for example. There are three main types of learning in machine learning. There's supervised, unsupervised, and reinforcement. Supervised learning, we have labeled data, right? So we know the outcomes of instances, and so we have examples with outcomes to train on. And so in supervised learning, we might do something like classification. So here we're trying to classify between outcomes of triangle or star, and the line here represents the boundary of the model in separating one class from the other. Or we might have regression, which deals with continuous valued outcomes. And so here the line represents the prediction itself. So this might be trying to predict height or weight, for example, as quantitative outcome values. Differently, we have unsupervised learning, where there is unlabeled data. We don't know the outcome, and here it's really more of an exploratory analysis, where we're looking for patterns between variables in our data set. So here we include methods like clustering or principal component analysis. So let's go back to artificial intelligence. Why do we care about it? Why are we focusing on it in this course? So there are many tasks which we might reasonably think requires intelligence. So for example, complex arithmetic, which we know is pretty easy for computers. But some tasks are easy for people, but they're difficult to automate in a machine. So an example of this might be facial recognition, right? We do that without thinking on a day-to-day basis, but it can be very difficult to get a machine to do this accurately and quickly. Same thing goes for interpreting text, right? We often take for granted our ability to derive meaning from text, but imagine how much harder it is for a machine when you think about all the background knowledge it needs to have regarding slang or possible typos or anything like that. All of a sudden, what seems like an easy task for a person can be actually quite hard for a machine. So AI is concerned with these difficult tasks which require complex and sophisticated reasoning processes and knowledge. So what is the promise of AI? Well, the first is automation, right? So in other words, we want to improve speed, efficiency, and the reduction of manual human effort. Of course, when we hear automation, it also conjures concerns about machines taking over people's jobs, which is a reasonable point also. Then we have scale, right? We want machines to be able to perform tasks that humans can do at smaller scales, but becomes impractical or impossible for them to complete as the problem gets bigger or more complex. Lastly, we have this desire to discover and innovate with AI, right? So how do we integrate information to find novel patterns, to design things, and produce new strategies? So we want to see if we can get computers to go above and beyond what human beings can do. At the end of the day, automation can be enough in terms of the value of AI. So here we have a cartoon where this gentleman is saying his decisions aren't any better than yours, but they're way faster. So imagine this is a clinician, and this is a machine learning model that's been trained to make predictions about whether or not to give a patient a certain clinical test, right? It might be that the machine doesn't actually do a better job predicting, but it might just work faster. It might be cheaper to use a machine. There are all sorts of reasons why automation alone can be enough without expecting the machine to do better than the human. Hopefully it doesn't perform worse, but at least as well can be really useful. So this figure outlines some of the major areas of study in artificial intelligence. And in this class, we're actually going to focus mostly on expert systems and some on planning and optimization. We're also going to learn just the basic framework of artificial intelligence, some basic themes including representation, reasoning, search, some of these things that make up modules of the course that are sort of the core background themes to understanding not just artificial intelligence in general, but things like machine learning that you'll get to learn about. So what are the fundamentals of artificial intelligence that this course is going to try and tackle? So in this cartoon, we can see some of these. We have logic, learning, neural nets, reasoning with uncertainty, search, and so on and so forth. Here's a sort of funny little meme encompassing what we've talked about so far, right? When people think about artificial intelligence, we usually think it's something really sexy and sophisticated. At the end of the day, artificial intelligence can be something really basic. I mentioned before, it can literally just be a bunch of if statements, right, that we pre-program to mimic some sort of human behavior. A lot of this course is going to focus on what we can call cognitive computers. Basically, these are things that simulate human thought processes in a computerized model. These things are made with computer algorithms. They're knowledgeable only about what they're taught or the information they're given. They can control only what we give them access to control. And they sometimes can continue to learn if they're given more data or access to environmental sensors. These can do very boring work for you, so they're great for automation. They can often make better, more consistent, objective decisions than human beings. And part of the reason is that machines don't have bias or emotional response or anything like that humans do. However, notably, machines can be biased based on the information we give them to train on. So they can actually learn our own biases if we're not careful. And they can perform tasks faster and without tiring. Artificial intelligence is largely dependent on experts. So for example, subject matter experts like clinicians, researchers, lawyers, machinists, insurance adjusters. At the end of the day, AI needs input from us. There's no AI that we can just set loose on the internet and expect it to be able to learn enough to complete some task on its own. However, these subject matter experts are usually not experienced in computer science or machine learning, and so to develop effective artificial intelligence systems to be applied to something like biomedical research, you'll need a collaboration between domain experts and AI developers. Cognitive computers are really another word for expert systems in the context of this course. And so briefly, I just want to explain what it takes to make one. And we'll get into a lot more detail about this later. But first off, you need content, right, from experts. You need knowledge from experts. Then you need to take this knowledge and you need to put it into an appropriate representation. You need a way for the machine to derive the appropriate meaning from that knowledge. Then we want to select or develop an inference engine for reasoning. So really the focus here is reasoning. We need to take this knowledge that's been represented and we want to reason with it. And then lastly, in a lot of expert systems, we need some user interface, right? So your everyday person who might not be an expert in machine learning or computer science can actually use this tool. So what might be an example of a cognitive computer? So imagine we want to make a tool that supports medical doctors in their treatment of disease. For example, IBM has its system Watson, and it was originally used on the game show Jeopardy, but it was adapted to tackle problems in oncology. So for example, it's been used at Memorial Sloan Kettering Cancer Center to provide oncologists with evidence-based treatment options for cancer patients. In particular, when medical staff input questions into Watson, it generates a list of hypotheses and offers treatment options for doctors to consider. Okay, so now we're going to switch gears and talk about this course itself, and we're going to cover the course syllabus. So first off, the course is broken into a number of modules. This first module is the introduction and background. Today we're covering the course and software. Then the next lecture will cover AI concepts in general. And then we'll also talk a little bit more in depth about Python coding and GitHub. And then we'll have a lecture on the history of artificial intelligence to provide context, historical context for everything we're going to learn throughout this course. I don't expect students to memorize any of this. This lecture is really meant to give you perspective more than anything. The second module is on logic, and we'll cover propositional and first-order predicate logic. Really, logic is something you can't do without when you're learning the fundamentals of AI. Logic incorporates a formal way for us to think about taking knowledge, representing it, and then reasoning with it, and generating, hopefully, useful new knowledge or making useful new decisions. The third module, we cover other knowledge representation strategies. So we go beyond the representations typically used in logic, and we explore some other ones, including semantic networks, frames, knowledge organization systems and ontologies. This is really useful for the biomedical domain. And then semantic webs and trees. So if you're familiar with the topic of decision trees and machine learning, this will be familiar to you. The fourth module covers the essentials of expert systems. So this is where we're really going to dive into the heart of the course, which is we're using expert systems as a framework to understand artificial intelligence systems in the biomedical domain. So here we start with a discussion of rules, which is really another representation, but we'll fit it in with an introduction to expert systems. Then we'll talk about a type of expert system called rule-based systems, which will really be the focus of what we learn in terms of expert systems in this course. Then the next time we meet, there'll be journal club style paper presentations from students. The following lecture, we'll talk about building an expert system and using Pike as a framework to do that. Pike is a Python-based software package for building expert systems. Then we'll talk about probability, really an introduction or a refresher to probability, as well as an introduction to uncertainty. So in the biomedical domain, when you're taking knowledge and you're using it to make decisions or predictions, not always can you be certain about information, right? We have to deal in probabilities. So in the biomedical domain, when we talk about AI, and a lot of domains really, uncertainty is a really important topic. And then we'll end this module by reviewing a number of biomedical expert systems that have been developed over the years, so you can get a sampling of some different examples. Module 5 will cover search. This is an important computer science topic in general. So the idea here is to learn, what is search, how is it important, how does it tie into artificial intelligence and the functioning of these algorithms in general. We'll start by covering intelligent agents and introducing the topic of search. Then we'll move into uninformed search and heuristic search, and end with the topic of local and population-based search. Module 6 will cover more aspects of uncertainty, and this will include entropy and information theory, Bayesian networks, and then state machines and dynamic models. Module 7 will cover some advanced and auxiliary topics with the remaining time we have left in the course. We'll start with a lecture on learning and planning. Then we'll give a lecture that introduces machine learning and will act as a precursor to the next AI course. And then we'll end talking about something that I actually study a lot in my own research, which is rule-based machine learning. It'll actually tie some of what you learned from representation and expert systems to the field of machine learning, and hopefully in an interesting and exciting way. And then the last day of class, we'll have final project presentations. Okay. Materials for the course. First off, I strongly recommend but do not require that you get this textbook, The Essence of Artificial Intelligence. It's a really easy to read, smaller textbook you can get on Amazon currently for about $18. I used it in part to develop aspects of this course, although in building this course I really had to draw from a large number of textbooks. Some other books, if you're interested, by no means do you have to get these books, but if this topic area interests you and excites you and you want to learn more, I recommend these additional texts. And then lastly, you will of course need a personal computer for this course, a laptop, a desktop, whatever. Okay, my expectations for students. First and foremost, please come to our class meetings on the dates outlined in the syllabus, having already watched the respective lecture for that day. I'm going to pre-record lectures and make sure they're posted online at least a week in advance. And as you watch them actively. Please take note of questions. I will have all the slides numbered. So if you come up with a good question and it has to do with a slide, note the slide number and just come to class prepared to discuss the topics of the day, ask questions. We'll also use these class times as a chance to do some demos and do some back and forth on homeworks and assignments, etc. When you come to these synchronous class sessions, come prepared to discuss that day's lecture and have some questions outlined. Also make sure to read the assigned materials. Again, the textbook isn't required, but I really do strongly recommend that you get that book and complete the assigned readings from it. It'll give you just another voice in terms of understanding the material that we cover in this course. And I think it's a very accessible book. So please do try and get that book and complete those readings. Additionally, I expect students to complete the assignments by the specified date found in the syllabus. But I'm flexible. If you have a hardship or there's an issue, just let me know ahead of time, and we can work out an extension if necessary. Lastly, I expect students to complete the midterm project and the final project. The midterm project is a journal club style presentation, and the final project includes a report and a presentation. Next up, how are students evaluated in the course? Students will be given a letter grade assigned according to the following proportions. 40% of the grade will come from completing the assignments. There will be 4 of them, so they're 10% each. You'll get 20% will come from the midterm paper presentations and discussion. 30% will come from the final project, including the written report and oral presentation. And lastly, 10% will come from class participation. So did you watch the lectures? Did you come to the synchronous sessions? Were you active in asking questions and participating in the discussion? All of that. Lastly, if you'd like, I'm going to offer up to 10% extra credit in this course for students that want to go a little above and beyond or want to bring up their grade if they're struggling, basically by helping me to make this course better now and in the future. So the identification of new and improved course materials, helping me make fixes if errors are found, or helping me to come up with new ways to communicate some of the ideas that we teach in this class, finding new reviews or readings that would be good to share with students now or in the future. Any of that stuff will count as extra credit in the course. A little bit more on the assignments in the course. Assignments will be a mix of reading and problem-based assignments requiring written responses or some Python coding, or both. The coding in this class is not meant to be very intense. However, I do try and incorporate programming here and there in this course so you get some experience using Python and experience using Jupyter Notebooks. So the assignments should be completed in Jupyter Notebooks. They should be clearly organized and use Markdown to enter in text so it's readable. All assignments submitted through Canvas should be saved as an HTML file for that submission. That allows me to very easily open them up in Canvas and review and grade them, etc. Before turning in your HTML homework file, please ensure that all the code, markdown text, and code output is properly visible within your HTML file. So do open it up before you submit it, look at it yourself, and make sure everything that you expected to be there is actually in that HTML, because otherwise when I look at it, I won't be able to view the content you put in there. And lastly, the assignment deadlines are specified in the syllabus. Next, we have the midterm journal club presentation. So this is really starts with a literature search. You can use this to kill 2 birds with 1 stone. So this can be an initial literature search to start to think of ideas for your final project. So you'll complete a literature search, identify a handful of papers, so like at least 3 original research papers that illustrate examples of AI topics covered in this course. So you can review the syllabus for inspiration, or you can just dig around with your Google Scholar or your PubMed searches, looking for papers, ideally that exist somewhere at the interface of artificial intelligence and biomedical research and application. These papers should ideally have all or some of the following properties. They're clearly written, they're impactful, they have clear figures, they clearly review relevant or related research, and they clearly denote the advantages and disadvantage of the either methods or applications proposed in their work. Next, you'll prepare a short 1 to 2 paragraph synopsis / evaluation of each of these publications, along with citation information for the papers, and save those papers as PDF files when you submit them to me. You'll turn in these materials by the given deadline. There's a date on the syllabus for turning in this first wave of midterm information. And then make sure that you rank the publications from the one you're most interested in presenting to the class to least. And what I'll do is I'll go through everybody's submissions and make sure that everyone has a unique paper that they're going to present for the midterm presentation. And then lastly, you'll prepare a journal club style format oral presentation with a maximum of 10 slides, and you'll give an in-class presentation of 10 minutes each with 5 minutes for discussion. The exact time will depend on the number of students so that we can make sure to fit it into one class, we'll probably end up pre-recording these presentations, assuming we're doing this class online at the time you view this. Some example topics, right, other than what you might find in the syllabus or included in the syllabus, include expert systems, clinical decision support tools, ontologies, standards in biomedical informatics, data harmonization, collaborative data analysis, and so on and so forth. I'll leave you to check these out. The final project, the purpose of it is to propose and attempt to implement a basic biomedical research or support tool to address a target biomedical task. So the simplest example of this might be use what we learned in the class to propose and try to build a basic expert system to make deductions towards some chosen biomedical task. So for instance, it could be a clinical decision support system or an alert system. It doesn't need to be really massive. The idea is to apply what you've learned in this course to propose and hopefully develop a prototype of one of these, of some kind of useful tool that falls within the category of artificial intelligence. You'll need to start by conducting a primary source literature search. Again, you can use that midterm project to kick this off, but you'll want to do some relevant background research and see what's been done before. You also need to identify any relevant data, databases, or necessary resources to help you develop this tool. The tool should be implemented in Python using and ideally use a Jupyter Notebook to clearly annotate the implementation and application of the system. So you basically want to provide documentation within the Jupyter Notebook so that when myself or classmates go through it at the end of the term, we can understand your thinking in terms of what this tool is, how it works, etc. For the final project, you can work alone or in teams or pairs, possibly groups. Again, just kind of depending on class size, but if you want to work with somebody else or other people, just let me know ahead of time so that I can work out groups and make sure that everything there is fair and goes smoothly. A little more on the final project. You'll include a final report and a 10 to 15 minute oral presentation on the last day of class. Again, depending on class size. This final report should be presented as a 6 to 12 page summary of the work. It includes sections such as background, materials and methods, the design of the proposed tool, a demonstration of the tool, sort of like a results section, and a discussion and conclusions section to summarize this work. Before you actually present the final project, about a month earlier, I'll ask for a final project proposal. This is basically a 1/2 to full page summary of your proposed project, just to make sure that you're on track to developing this tool and laying it out to complete your final project. Again, the final report and oral presentation are due the last day of class. Okay, now let's move into introducing and installing Python and Anaconda. So Python is a programming language, a very accessible and largely easy to use programming language. Python has both back-end and front-end development support. And what I mean by that is front-end refers to what the user sees. So it's some sort of user interface where you click buttons or you can scroll or anything like that. It's basically what the human being interacts with. And the back-end is all the code behind the scenes that does all the work. Python is a cross-platform language, which is great. You can use it no matter what operating system you have. It's open source. There's a strong community base. Has tons of tools that you can use and just load up. And in general, it requires fewer and simpler lines of codes to program stuff. So it's really handy, especially for somebody who isn't strictly a computer scientist. Some of you might use or be familiar with R as well, or only. And just to kind of contrast, why you might use one or the other or the major differences. So R, in terms of scope, is used mainly for statistical modeling, and Python is used for all sorts of things, including web application development and data analysis. Typically, R is used by statisticians, analysts, and data scientists, and Python is typically used by developers, data engineers, and data scientists. R is suitable for people with no prior experience in programming, although there is a bit of a learning curve when you first get started with R. And Python is also great for newbies, but also it's powerful enough for experienced professionals and coders. If you're looking for packages in either system, packages in R come in something called CRAN. That's where the packages are managed and curated and standardized. And in Python, it's something called PyPy. And then there's different visualization tools available for both. These are packages for visualizing data and results and so on and so forth. If you want to learn more about Python, these are some of my favorite books that I've come across in recent years. So if you want to get a textbook, these are ones I might recommend and start with. When you go to install Python, you generally have a couple options. The main Python versions right now that people might use are either Python 2 or 3. In general, just use the most recent version of Python, which will be a variant of version 3. The only reason you'd want to run an older version is typically if somebody coded something that was only designed for an earlier version of Python. But no one in this class should run into that issue. Another thing to consider when you're installing Python is whether to go with a 64 or 32-bit version of Python. And this choice is primarily based on your own hardware architecture, so what CPU you have, and what operating system you use. 64-bit processors can run either 64 or 32-bit operating systems as well as Python installations. 64-bit processors handle large amounts of random access memory, or RAM, more effectively. So in general, just choose the 64-bit Python unless, again, there's code that it was designed to be run on a 32-bit system, which, again, I don't think anyone's going to run into that issue in this course. As I alluded to before, Python has a huge ecosystem of available tools and packages. So there's really very little need or no need to reinvent the wheel, right? There are tools to do most everything you'd ever want, and it's just a matter of importing those packages and learning the basics of how to call them and use them. To make your lives simpler, there's this package called Anaconda, which is a great way to sort of install most everything you'll need at once and organize it. So Anaconda is a free open source software distribution of Python and R, as well as associated packages for scientific computing, in other words, data science and machine learning. So one easy way to install Python and keep it up to date along with all these packages you're likely to use is to just install Anaconda and occasionally update it. Anaconda includes things like Jupyter Notebooks, which we'll use in this class for writing Python code, running experiments, and communicating your work easily to others. Then there's a package Pandas, which is great for exploring and manipulating data. A package called NumPy for performing numerical operations on data. Matplotlib, which is great for making visualizations of your data, plots, etc. Scikit-learn, also called sklearn, which is used for building and analyzing machine learning models. And TensorFlow, which is a tool for parallelization of analyses to more efficiently handle big data. If you're newer to computer science and programming, it's useful to cover some basic definitions regarding Python coding. First off, the term package is a collection of self-contained code that someone else has written and it does something, right? So it can, run a machine learning model, it can create visualizations. Basically, it's just something you call and use and you don't have to program from scratch. Conda refers to a package manager that helps to install, update, and remove packages within Anaconda, or really just Python packages in general. You can also use a package manager called pip, which I think also automatically installs with Anaconda. If not, you can install it yourself. There's a link to some more information about pip right here. And it's just an alternative package installer for Python. The term environment refers to the specific collection of packages or data science tools being accessed by your code. So when you write code to do something, if it calls different packages to do things, your environment includes what are those packages you call and what versions of those packages did you call. So if you want to reproduce some analyses you did, you'll need all of that information. If you want somebody else to be able to run your code, they'll need to know exactly what you used in order to replicate what you've done. The build of a package. This refers to the Python version that the package is made for. And then the term scripts. These are just, as opposed to a full package, a script is usually just one Python file in this case, and it's some kind of reusable code. It can be imported or saved as a Python file, and they have the file extension .py. The term working directory, this is the directory from which a specific piece of code or software is run. Usually the working directory is the project directory or the folder that includes, the Python file that you're trying to run. So code that is run, so if you have a Python file and you run it from the working directory, that code is going to automatically look within that working directory for other files it needs. The command line interface, or CLI, this is a way we can interact with the computer with text commands. It's generally faster and you have better control and management for working with larger data sets than you would on a GUI or something like Excel. Here's a link if you want to learn more about command lines. So it'll answer questions like how to open a command line interface on Mac, Windows, or Linux, and it'll talk about some of the basics on how to use a command line interface. Lastly, we have graphical user interface, or GUI. And this is something that allows us to interact with electronic devices through graphical icons and visual indicators instead of command lines. Lastly, there are different Anaconda products that you can download and use. Apart from the full Anaconda package that we already talked about, there's also Miniconda, which is basically just the bare necessities of Python and Conda itself, the package installation and management tool. Also, there's something called Anaconda Navigator, which is a GUI to help manage packages without having to do it from the command line. So if you're not terribly programming savvy, there's some nice tools out there to make your life a lot easier. Okay, to install Anaconda, I've provided some links here to help offer guides on how to install it based on the operating system and computer that you have. So please feel free to check these out if you're not familiar with installing Anaconda or you don't already have it. Okay, coding environments. We'll spend a brief amount of time on this. We hinted at this idea that, if you make some software and you run it and you want somebody else to be able to use it or reproduce your results, they're going to need to not just have your code, but need to know the environment of that code. So if we have user 1 here and they created the code, user 2 might not be able to run it unless they know that environment. There's a number of ways to manage custom environments on your computer. If you need to make sort of a temporary environment to do a specific task or repeat something that somebody else did with their software package, you can create a virtual environment. This is a local project environment that can be activated as an alternative to your base environment, which is typically installed within the path of your computer. And the path is an environment variable on Unix-like operating systems, DOS, OS/2, and Microsoft Windows, specifying a set of directories where executable programs are located. It basically tells your computer where to look for software that it's going to use again and again, so you don't always have to tell your computer where to look for it. It'll just automatically know my user wants to use Python. We already know where it is. We're just going to use it. So the virtual environment, though, lets you switch between this base environment and sort of these temporary environments, and you can activate them. You can save these temporary environments in folders. They'd be shared as files, so this is something you can learn more about if you would like. But for the purpose of this class, you probably don't need to learn much about this, but I just want to provide some context. If you want to distribute your software that you create with the environment, you can actually build an environmental file starting with Miniconda, right? Since it's just the bare bones version of Python and Conda, right? You can add manually the packages that your software will need so that when you share your software and the packages it requires, there isn't all the bloat of everything in Anaconda, so it doesn't take up extra space unnecessarily. If you want to learn more about Conda documentation on managing environments in Python, I've provided this link. Okay, Jupyter Notebooks. So these are a scientific notebook like you might use in a laboratory, but for code. They're basically an open source web application that uses a GUI and allows you to create and share documents that contain live code, in other words, code that you can run right in the document, equations, visualizations, and narrative text. Here's a link to learn some basic information about how to install and use Jupyter Notebook. This is an image of the GUI that is Jupyter Notebook. So this is what you'll see once you open it up. Jupyter Notebook files are saved with this extension, .ipynb. To open one of these files, sometimes you can just double click on the file and open like any executable, but sometimes depending on how you set up your initial environment or how you set up Anaconda, that doesn't work. There's little tricks you can look up online to get that to work. But if double clicking on the file doesn't work, the more traditional way is to use a command line interface to start Jupyter Notebook up. And so if you've installed Anaconda and the Jupyter Notebook files within your main path, usually what you can do is just open up your command line interface, type Jupyter Notebook and click enter, and it'll open the Jupyter Notebook in a window automatically. Alternatively, when you install Anaconda, it usually comes with this software called Anaconda Prompt, and so you can open that, and it's basically a command line interface that is guaranteed to have Anaconda ready to go in it. So you can open that up and type Jupyter Notebook, enter, and it should definitely work in that situation. Once you've opened it up, right, this is what you might see. It'll show you the working directory within which you opened up Jupyter Notebook, and you can navigate to the appropriate folder if you're not already there. If you want to create a new Jupyter Notebook file, you would just click New over here. Once you click it, you'll see something like this pop up, and you can choose Python 3, assuming that you want to do something in Python. You'll also have the option of R, depending on how you set up Jupyter Notebook, if you want to do something in R. And then you can name the file from something other than untitled. A little bit more background on Jupyter Notebooks. In the notebook, you'll have cells, right? These are the basic places where you'll put in information, either text or code or something else. You can have a code cell. It contains code that can be executed by the kernel. And once you execute it, it'll display the output of running that code right below the cell. Alternatively, you can have a markdown cell. And basically, this is just a place where you can put formatted text. And if Markdown is really a useful thing to learn, both in the context of R or Python and Jupyter Notebooks. And if you want to learn more about how to write in Markdown, check out this link. It's something you'll get some experience with in doing the homework assignments. So this might be useful if you've never done it before. Kernels, I mentioned before, this is the computational engine that executes the code contained in the notebook document. To run a cell using a kernel, you just click this button in Jupyter Notebook. Also, you can go into the options for kernel, and you'll have these options of restart, restart and clear output, and restart and run all. Also, here's some information about Jupyter Notebook shortcuts that you can use that are great to know. So as you use it for homework assignments or in general, if you don't already know these tricks, this is some really helpful information. Okay, and I like to end most of my lectures with a meme and a quote. So here we have, by far, the greatest danger of artificial intelligence is that people conclude too early that they understand it. Just a heads up that the first assignment is available on Canvas. This first assignment will have the following goals: to get your computer set up and equipped with the tools needed for using Python and the available packages, to understand the difference between Anaconda, Miniconda, and Conda, to understand how to access Python through your terminal or command line, to learn how to use Git and GitHub, and also to learn some of the basics of Python program if you don't know them already. If you're already really savvy at all these things, this assignment will be super easy, and if not, it'll take a little bit of time, but again, it's not meant to be terribly advanced. It's really a lot of the basics that you'll need for this course. And with that, thank you for your attention. I will see you in the next lecture.